Okay, so last day when we were looking at antiderivatives, we also called those indefinite, meaning there was no bounds for them. We just came up with this equation and we had the constant that was left over. No, I'm not going to chase them anymore. Today we're going to take a look at one of the major applications for what we study integrals for. And we're going to start by building up a bit of background. So this is something that we're going to do quite a bit and we'll practice more. But today we're going to kind of get an idea where this comes from. And it is something the AP exam likes to test you on. And we'll see this a bit more, as I said, with a bit of practice. So there's a couple ideas we want to start with by trying to figure out how this is all going to work later in this block and the second one. The first here is we want this idea of a lower bound. Whoops, hang on, we'll have to start again then. Shoot. Okay, so we want this idea here to be the lower limit. And what I mean by this is if we were to try to approximate area under a curve, like this one here is the exact value, and it's a nice shade underneath the curve. But if we wanted to estimate a lower bound, we could do it by placing rectangles underneath the curve because it's easy to get the area for a rectangle. If we added up all these rectangles, we'd have an approximation. Now this one's called the lower because everything that we pick comes underneath the curve, so I'm missing this space here. All these little spaces means I'm going to be less than the actual area I was looking for. Okay. On the other side of things, we have this upper bound. And what happens there is I have these extras. I always pick the largest value to make my rectangle. So I have all this extra space, which means this approximation is too large. But the real value will be somewhere in the middle. Okay. So we'll try doing this with the curve to see kind of how it works. For example, if we wanted to do the upper area and get an estimate for the area for this curve, if we use 4 rectangles, and we go from 0 to 4, then how wide do you think each rectangle is going to be?
1 space wide.
1, right? Because there's 4 units, so it's going to be, each one of these here would be a rectangle. And I want to do the upper limit, which means when I look at my choices in this range, I want to pick the largest value for the height of the rectangle. That way I have the biggest possible area. So if I go up, it turns out that's actually the largest spot. So that would be my first rectangle. Then the second rectangle again, I'm looking here. Where's the largest spot? Well, there's an upper bound like that. And if I keep going, this would be my upper limit to the area. So with 4 rectangles, it's not going to be a great approximation, but it still gives us some idea. So how could we come up with the upper limit? Well, let's just do some basic area math here. Each one of these has a width of 1. Here the height is 16, so it'll be a 16 for the area. This, yeah, it does touch 16, right? And then this one here, this rectangle has a height of 15, so 15 times 1. This one here has a height of 12, 12 times 1. And this one here has a height of, what's that going to be then, 7? 7, okay. So if I added up my areas, I can say without a doubt that whatever the area under that curve is, it must be less than this total. So let's see here, that looks like 50. Yeah, 50. So we know that well, yeah, for this example because we use rectangles, but we know the area under the curve. I'll call this A. A must be less than 50.
Oh, yeah.
Okay. So then we can get the lower limit and to try to get us an idea what it's between. So we're going to do the same approach. Let's just see if we get the idea of a lower limit here. If I pick the smallest rectangle I can, meaning the shortest one, the lowest rectangle, then what will its height be in this range? give you a hint. It's larger than 10, smaller than 20.
15.
It's 15, yeah. So if you look at your choices, this is the curve. Here's the smallest spot on the curve right there. So the smallest rectangle I could make would go like this. Okay. And if I keep going in this pattern, here's the smallest spot here. Here's the smallest spot there. And this one, unfortunately, won't get any area. But you notice that it's all underneath the curve. So I have a lower bound here. There's area missing. So again, if I add these up, the width is 1. For the first one, the height is 15, so the area would be 15. Then the area would be 12, then 7, and 0. So my lower limit would be 15 plus 12 plus 7 plus 0. Adding this up, I'd have 34. So what I can then say from the two things we just did is that the area has to be somewhere between 34 and 50. How could we get a better approximation?
Averaging.
Okay, we could maybe guess somewhere in the middle, but remember with the curve, things don't necessarily happen nicely like an average would give us a nice number, directly between the two. It may be the case that it's a better estimate, but it may not be good enough for our purposes. So like what if I said to you, I want this to be accurate to within 0.1 of a decimal?
Smaller rectangles.
Yeah. So what happens to the rectangles if I make them smaller?
They get narrower.
Sorry, keep
Narrower.
narrower. Yes, that's obvious because they're smaller. Say it.
The area is smaller.
The area for each is smaller, and then part of the thing is these gaps here are going to get smaller too. So for example, if I put more rectangles, let's just say in the next one that I use 2, well there's a lower limit. So instead of having all of that space, I've now gained that little bit of extra. So as I double up and I make more rectangles, I'm going to get more and more accurate. Does that make sense? Right? We'll have less area that's been missed, like here, and less area that's been overestimated. For example, in this one, it would go like this now if I doubled it up. And now it's just this part, I've gotten rid of it. So they get more accurate as we use more rectangles. And that's the idea that we're going to build on here. So what do you think would happen if I could use as many rectangles as I want? Do you think it would matter if I use an upper bound or a lower bound? Anybody think of what's going to happen here in these two pictures? Like let's say I used 1 billion rectangles. 1 trillion rectangles. A Google rectangles.
Wow. Google isn't a number, it's a search engine.
It's both, actually.
What? It is?
So what do you think is going to happen then? As we get bigger and bigger numbers, what do you think will happen? Yeah, and it doesn't matter which one we picked, because whether we pick the upper bound or the lower bound, if we pick an infinite number of rectangles, so I'm going to say n is the number of rectangles, then the limit as n goes to infinity of the upper limit is equal to the limit as n goes to infinity of the lower limit, which is equal to the area. So the idea is important because it will give us some freedom. Because, let's put it this way, the worst overestimate you can make is the upper bound. The worst underestimate you can make is the lower bound. And even if I take the worst of my estimates, it still goes towards the same area. So the freedom is that we can pick a point anywhere we want. If the worst that's overestimate and the worst that's an underestimate still gives me the area, you can pick any point in the middle that works good for you. It doesn't matter where we pick the points. If we still have an infinite number of rectangles, we will get the true area. So that's going to be important for us to find the last benefit, which I won't tell you just yet. But
So is it sort of like Newton's method?
well, no, but for now what I want you to do, we'll learn some numeric methods later, so you're probably thinking correctly there about, it's not Newton's method, but there are some numeric methods for doing this. I'm going to show you one here, but just so I don't cram it in there, I'm going to open it up on a new page. You'll probably be able to do it here. And you also need your textbook. In this section, there's some formulas that I'm going to use here. So I'll just pause this while you get your textbook. So this is first what we want to do is we're going to be able to make a formula that will give us an approximation for a certain number of rectangles. So to do that, what we want to figure out is we're going to work to build up this formula here. We're going to build up a sum of the height times the width, which is going to be the sum of the rectangle that we, sorry, there's a t in height. The rectangle that we are going to pick will have the same height as the function. So it'll be the function at a point times the width of the rectangles. So here this is going to be the width of the rectangles. And this is going to be one of the points. We can pick any one we want, so we'll pick left or right. It's not always going to be the case that one will be better than the other, but usually there's some advantage. So for example, in that parabola that we're dealing with, if we think about it like this, here's the parabola, and I want to put my rectangles in it from 0 to 4. Okay. Let's just say that I had 8 rectangles. How wide will it be? Each one will be how wide? 0.5. If I had 16 rectangles, how wide would they be? A quarter. So how are you guys getting those answers that are figuring this out? Taking the amount of space, dividing it by the number of rectangles. So it would be 4 minus 0. And we're going to call the number of rectangles we use just n. Okay. So in general, if we had a range from A to B, what we would do is we'd go B minus A over n to get my width. Okay. So are we okay about how we get the width of a rectangle? Possibly? Okay. Now what I have to figure out, if I know how wide each rectangle is, I have this piece of my formula. I got to figure out how tall each of the rectangles is. To know how tall it is, that has to do with wherever I am, right, on my function. Like maybe this is my rectangle, okay, and this is the height here, where this is my point. So basically, if I can find out where this point is, that I basically means it'll be like point number 5, or point number 2, or point number 1. I have to figure out where all these points are. So for example, the first point, if we were to do it with the right side, the first point would be 0. Then I would move over by delta x, and I would be at 0 plus delta x. Then I would move over again, and I would be now at delta x more, so 0 plus 2 delta x's, because I've just moved over again. So I can find each of these points. I mean, the next one's going to be here. This will be at 0 plus 3 delta x. Can anybody see the pattern that's sort of emerging? Hands up if you can, just so that I know that, yeah, okay, it's not easy to come to calculus first thing in the morning. So this pattern that's emerging is showing me for the, sorry, I said right, but this is actually the left side, right? I mean, that's the left. So we're going to use the left side here. And each point, and we'll call it at position I, is, for us it'll be 0 plus, let's see here, it would be I, whoops, don't need a bracket there. So it'll be 0 plus I delta x. Okay. So here's point 0, where we start, point 1, point 2, point 3, and so on. So that means this point here, you add 0 delta x's, 1 delta x's, 2, 3, you keep going. Okay. So in general, if we had to do it this way, This would be our A, this would be our B, so the left point would be A plus I delta x. So we're not going to do, I'm just trying to build this up to you. We won't spend a ton of time doing area this way, but it is a way that people do it sometimes. More famously, this would be known as a Riemann sum. Anybody heard of Riemann? All right, watch a few math movies. You'll hear his name mentioned, like Beautiful Mind and Good Will Hunting, that kind of stuff. But now that I know where the points are, then that means for us, I mean, we don't need to add this 0. Basically, what I want to do is I'm going to evaluate it at f of I delta x is the height. So if you told me, like, what's the height for point number 5? It would be 5 delta x. What's the height for point number 10? Then it would be f of 10 delta x, right? So now I can try and put these back together in this formula, and I'll try and describe it for you as I write it down. Okay. It's going to be the sum, and I'll just write this down again to keep it in perspective what we're doing. It's the height times the width. We start at I equals 0. And we're going to have n rectangles. So this is going to be the sum of all my pieces will be the sum from I equals 0 to n of f of, I'll call it xi times delta x. Okay. Where this is, for us, we're using the left side, and this we're using the width. You could also do it with the right side, or anyways, but if I then substitute them in, my function was this. So our formula would become negative xi squared plus 16 delta x. And how do we get those xi's? Well, we said it was going to be at I times delta x. So that's what I'm going to substitute in. So this is I delta x squared plus 16. And we already have a formula for delta x. We set up here that it represents the width, and it was, for our purposes, 4 over n. So I'm going to substitute that in, and it's going to be the sum from I equals 0 to n of negative I times 4 over n squared plus 16 times 4 over n. So to finish this off, my formula for, you give me any number of rectangles, this formula would sum it up. It's going to be negative 16I squared over n squared plus 16 times 4 over n. And finally, that's going to be negative 16I squared. Sorry, oh, it's not a 16. It's a 64. So I'm just going to multiply this one in. So it'll be 64 over n cubed plus 64 over n. So that formula would tell me for any number of rectangles that you give me. You might say, well, let's try it with 10 rectangles. N would equal to 10. I want to try it with 1,000 rectangles. N would equal 1,000. And there are some things that, you know, even with the techniques we have, we still have to resort to a numerical approach. like we would stick this into a computer and have the computer spit out a million rectangles, right? Because we don't want to do this by hand. But I'll show you how we can also find the exact value. The exact value was the idea we just said, is what happens if we make an infinite amount of rectangles. So in this formula, then what I'm going to get when I work this out is, how do we get rid of this? Well, fortunately, there's been quite a work done on those formulas on page 288 that I asked you to look at. There's one there for the sum of I squared. So the sum for I squared is going to be, I can replace this. I can make it, put in a new slide here. I can make this the limit as n goes to infinity of negative 64 n times n plus 1 times 2n plus 1 all over n cubed. And this one's, this sum here, there's no I in it, but it's going to happen n times, right? So if it happens n times, because it goes from 0 to n, it would be 64 over n times n. And you can see that in, that's number 1 in the formulas in the textbook. It says take some constant, and then you'd have sum the constant. It's the constant times the number of terms you summed. Okay. So for us, if we were to work this out, we get the limit as n goes to infinity. Okay. And those n's would disappear, so that's nice. So on this side, let's see what we get. We get negative 64, and I'll have 2n cubed plus 3n squared plus n. So we've done this kind of limit before. Fortunately, it's not a, hold on a second here. Let me just make sure that n for delta x. Okay. So I've got 128 n cubed over n cubed plus, what's that, 190, sorry, it'll be minus 192. So minus 192 n squared over n cubed minus 64 n over n cubed plus 64. So what happens to these pieces now? Well, as n goes to infinity, the bottom wins, and all that I'm left with is the ones where the n disappeared out of it. And so one thing I forgot to put into the formula here was there's a divide by 6. So that's why I was looking ahead thinking, uh-oh, this is going to turn out to be negative. Just means there'd be 6's in those positions. Okay? So if you added a 6 to all those pieces, it hasn't affected our answer yet so far. It would have had a big effect otherwise. But now that I'm here, the only things I was left with was negative 128 over 6 plus the 64. So I can actually get, this would be if I use an infinite amount of rectangles, which, I mean, it only happens in fantasy or in calculus, right? 128 divided by 6, and take 64 off of that. So we'd get 42 and 2/3 as the exact amount of area underneath that curve. Okay? So fortunately for us, people have decided that that's terrible. Yeah, terrible, yes, terrible, okay, I agree. We have better techniques because this is so terrible that we've come up with ways of doing it. Unfortunately, the technique only works well, it works for many situations, but there's also many it doesn't. And from now on, if we can't do it, we would resort to a calculator or a computer to help us. Question?
Are there more situations where this won't work or where it will work?
Well, let's just say there's infinite of both, but I don't know which infinity's bigger. I don't know. But we'll address that later in the unit. You'll see exactly what I mean once we get there. But for now, let's come up with a better technique and figure out how to save ourselves from, you know, I don't know, I wouldn't say shooting ourselves for taking calculus, but we won't do this limit process. The point is we can pick an infinite amount of rectangles, and we've seen that it doesn't matter where we pick our points, whether it's the upper bound or lower bound, an infinite amount will still go to the area that we're looking for. So the proof, I don't want to do the full proof for you because the proof is a little challenging, but I want to paint a little picture for you of how this connects to what we're doing. If I can pick infinite amount of points, and I can pick any point that I want, I just want to sketch a picture for you of a smart place that we would pick points. So let's just say this is my graph, and let's just say you've picked these, I don't know, they can be any shape rectangles you want, right? It doesn't matter where we pick them. Once we make an infinite amount of these things, they'll all converge to the same area we're looking for. So I could pick these points here. So let's say this is, let's say that was x1 and that was x2. And I could use those for my heights, right? We had this f of x1 and all that extra stuff. But if we know this curve is differentiable, we have this extra feature, differentiable. We have this extra feature that the mean value theorem says. By the mean value theorem, there must be some point in the middle here, so let's call it C, so that f prime of C will be equal to f of x2 minus f of x1 over x2 minus x1. So instead of picking those points we had, we're going to rely on this fact that I can find the derivative there somewhere in the middle. That's going to be the secant line, the average height, right? So this represents the average height. So then what I'm going to do is instead, I'm going to take a sum using that point, and we want something that describes a rectangle which is like a sliver. It's infinitely small, and we have something for that. We've been calling it dx, right? As we take a derivative, that dx goes to 0. So this is what we're actually looking for. We're going to reuse this, which it goes to 0, so those infinitely many rectangles are there. And this looked like something that you might have been working on if I was to change this. Does it look like anything familiar right now? Your cognitive load is just through the roof, right? Antiderivatives, right? Yeah, so that's where I want you to, that's as far as I'm going to take the connection with you. If I was to integrate this, I get back to the function, right? Taking its antiderivative. So let's take a look at how that connects to area. Okay. If I wanted to figure out the area, now I'm going to have to do it. We're going to put bounds on the integral, and it's going to be f of x times d of x, or the antiderivative at b minus the antiderivative at a. So I'm going to paint a geometric picture for you, and those of you that your cognitive load went through the roof and you'd shut down, this is where you can wake up, okay? I promise this is the part where it's going to be friendly, and you will see where the connection comes in. But we need to know a little bit about where it comes from, because this is a huge idea in calculus. This is actually something that's called the fundamental theorem of calculus. It's so big. Okay, so that's why I had to torture you for just those 20 minutes. It is really important to calculus. So let's take a look at what we already know from geometry and figure out the area underneath a curve from -2 to 1. So from -2 to 1 on this curve, there's -2, and there's 1. This would be the area that I'd like to find. And we can do that without any calculus, because there's two triangles there. Okay? So can somebody tell me how much area is in this triangle here? It's 1. It would be, it is a width of 1 and a height of 2. So altogether, 1/2, 2 times 1. The area in there is 1. Okay? What about the other triangle? How much area is down here?
4.
4 is so close.
6.
Well, let's go to the geometry then. How tall, I guess, is that rectangle?
4.
Ah, why -4? It's going down. Remember, this all comes from rectangles. What would the height of this rectangle be if I drew it? It would be a negative, right? Because it would be a negative number, that means what we're adding into this would be a negative as well. So it would be -4 because the rectangles we're going to draw would be down. They'd be underneath the x-axis. So it would be -4. The width here would be 2. So it would be 1/2 times -4 times 2, which would be -4. So using the areas of a triangle, the area would be the bottom triangle plus the top triangle. I should get an area of -2. Oh, sorry, it's supposed to be a 1. I should get an area of -3. Okay, so it was this triangle plus this triangle. Now let's try it with an antiderivative. Okay? So this would be the antiderivative. And here's the notation. It goes from -2 to +1 of 2x. And when we find it now, the way we usually write it would look like this. It would be x squared, and we write this bar to say evaluated at -2 and 1. So if I was to do this, again, this is where we talked about it coming from. It's going to be 1 squared, take away -2 squared. The antiderivative at 1, take away the antiderivative at -2. Magic. Okay. So it ends up being the same number as if we did the geometry. So that's what we're going to try for a couple, because it's really important that you don't just go into autopilot and think, oh, if I need area, I need an antiderivative. You got to remember this connection. So we're going to try it for a couple more pictures. For example, I don't know why this always prints so poorly, but this is supposed to be 1, and this would be a 3. So first of all, this is asking us for the antiderivative of 4. So let me show you what that would look like. And we're looking at it from 1 to 3. So what's the area going to be?
I just have a question. When evaluating with the antiderivative, do we have to worry about adding a constant?
Oh, that's a good question. I may have blown over that one. So the question was, do we have to worry about the constant? And the answer is no, because if we were to do a constant and we take away the antiderivative at the other point, same function, same constant, when we subtract them, they would disappear. So the answer is no. When we do a definite integral, we don't need to worry about the constant. They would cancel out in this calculation. So that's a great question. Okay, but anyway, back to this one. So what does this mean when you read it? Remember how I said in derivatives, you have to think two things. Whenever you see a derivative, you're remembering that it's rate of change at an instant or the slope of the tangent, right? For an antiderivative, if you read this, what are you thinking in your head when you read this right now? What's it trying to find? Well, 4x is the antiderivative, but what does it represent? What's the picture trying to represent that we're drawing?
Y equals 2x.
Okay, well, it's the area that we're looking for, right? We're looking for area. So when you see this, your antiderivative is representing area. Number one, when you see it and you're trying to make sense of what it is, we're representing the area underneath the curve between it and the x-axis. Okay, the other thing to remember here is it's also representing an infinite amount of slices. It's a sum that we've sliced up all these infinite little rectangles. So I got a really good example for you next block of how this works, but you really want to remember both of those. Not just that it's the area, but it also does an infinite sum for you. Because there's sometimes when a problem makes more sense if you think about it not as area, but as an infinite sum. Because sometimes that'll make more sense. In this problem, though, we're just focusing on area. Okay. So what would the area be according to the geometry? Yeah, so the width here is 2. The height here is 4. So the area would be 8. Okay. If we were to use the antiderivative from 1 to 3 of 4 is 4x evaluated from 1 to 3. Okay. That will be 4 times 3, take away 4 times 1, 12 take away 4, which is 8. So 8, just like the geometry confirms, it's found the area under the curve. So I'd like you to try the next one on your own. Draw the geometric picture. What is this picture representing? Okay. From the picture, find the area, and then use an antiderivative to confirm that they do, in fact, give you the same value. Oh, there's 0 and 3. Yeah, sorry there. That's 0 and 3. Okay, so what you should have a picture of is, this would be the line x equals to 2. And I'm looking for the area from 0 to 3. So this would be, say, 0. This would be 3. So what it's going to do then is it's going to try to find the area of this figure. Right? If we wanted to do it geometrically, well, there's two geometric pieces in here. There's a triangle and a square. So the area for the square, that's 2. So its height is going to be 2 by 3. So this would have an area of 6. Then the triangle here, that's the point 3, 5. So if that's at 5, the height is 3, the width is 3. So the area for the triangle is going to be 1/2 3 times 3, which is 9/2. So 6 plus 9/2, it's going to be 10.5 or 21/2. If I use the antiderivative instead, from 0 to 3 of x plus 2, I get x squared over 2 plus 2x evaluated from 0 to 3. Now this one's nice because when I put in 0, everybody just disappears. So the only calculation I'm going to have to do here is going to be 3 squared over 2 plus 2 times 3. Take away, it would be nothing. So I get 9/2 plus 6. And look at that. Isn't that strange? Those are the same pieces we had here. So they will in fact add up to 21 over 2 as well. Okay. So in some cases the antiderivative is going to be easier than the geometry. And in some curves it's not going to be possible that we have a nice geometric formula for it. Okay, so you try, don't worry about the geometric picture anymore. But what I want you to do is try finding these antiderivatives here. Okay. Okay, evaluate them and tell me what the area under those curves would be. Those are curves we would not have a geometric formula for. So you already have a powerful tool of finding the area. Question? Oh, sorry, yeah, here. You know what, I'll zoom in on them, maybe that'll help. Let's go like this. Is that any better? It's a 1 and a 3. And this is a 0 and a 4. Okay, so for the first one's antiderivative, you should have 2x squared minus x cubed over 3 from 0 to 4. Now, if you put this into your calculator as y1, then you can use your calculator to go y1 of 3, take away y1 of 0. Sorry, it's a 4. But that may be faster than doing it the long way. Sometimes it's faster to do it the long way. It depends on what function you're using. So in my calculator, 2x squared minus x cubed over 3. Let's see here. So I end up with 10 2/3.
Wait, 10 to the power of 2/3?
No, 10 2/3. So you could also write it as 32 over 3 if that's easier. Okay, so I'll give you another minute in case you're working on that next one still. So I end up with 4/3 here. Okay, so the last thing that we're going to take a look at today is a couple of rules, and these rules will be easier to understand if you think geometrically about them, and you think about the picture. So for the first one, if I take the integral from a to b, and then I flip it from b to a, this negative sign has to be put in there. Can anybody think of why going backwards now would make it negative? There's a pretty simple answer. It has to do with those rectangles that we were making.
It goes upside down.
It may not go upside down here. We're going backwards, so it's like instead of going from A to B, now I've turned around and I'm going from B to A. So think about, how did we calculate the area with those rectangles? How would that change this to be negative?
It's backward.
Backwards, but
You subtracting the different part.
I'm subtracting those parts, but there's like a, look at that, think about that formula for area. It's the function's height times the change in x. So why is it negative if I go backwards? Yeah, the change in x is negative, right? Before I was going forwards to get to where I was going. Now I'm going backwards, so the change is negative, which means I'm going to end up with a negative area if I go backwards. Okay, so that's one thing that's you got to remember. The other thing is, it may be convenient to split at a point. So for example, let's just say that there's somewhere in the middle that's convenient for me to break it up, like a piecewise graph. So I can split it up at this midpoint, which I've called M. So I will draw you a picture of that. I'll put it back if you didn't have a chance to write it. But imagine you had a curve that went like this. And let's just say it went like that. And it's a piecewise graph. Then we could find the area under this curve as one piece, and then the area under this curve as another. So instead of going right from A to B, which would be difficult because the function changes, we would stop here in the middle and do another integral. So we can split it up like that, adding those pieces together. So here's a couple of examples that sort of illustrate these rules. Okay. Now, going from 0 to 3, let me just, for a heads up here, this is the one we've already done this. Where did we do it? Here. We've already done it, and we found out that the answer was 21 over 2. So we already did it. This time we're looking at it. I'm just saying I don't want us to necessarily go through all the math. And we've reversed the integral. So we can just say that's the same as the negative if I went from 0 to 3 of x plus 2, which is equal to negative 21 over 2. See previous example. So it's the same area, it's just we've gone backwards, so the delta x is negative, means the area will be negative. The second example of where it's helpful to know these rules is the absolute value graph. The graph itself is not very, it's fairly tame, but it changes, right? It does that, there's some strangeness there. If I wanted to know the area from negative 1 to 1, it's probably more convenient for me to write this as the integral from negative 1 to 0. And if I look at this piece here, that piece is negative x, plus the integral from 0 to 1 of this piece, which is x. And now I've been able to break it up as a piecewise graph so that I don't have to do it all with absolute values. This would be negative x squared over 2 from negative 1 to 0 plus x squared over 2 from 0 to 1, which will give me 0 minus negative a half plus 1/2 minus 0, so I end up with 1. So again, if you're thinking geometrically, the last thing you might want to think about here, there's actually no calculus to do if you give it some thought before you start. Here's what the picture looks like. Any idea what the area from 0 to 2 pi would be?
0?
You're right. How come?
Because it cancel each other out.
Yeah, so here's the hole. Here's the mound of dirt. The dirt fills in the hole. So together, they would end up canceling. We would end up with 0. Okay. So for a graph that you know has that symmetry, same amount of area above as below, there would be a 0 there. Okay. So I'll give you some extra time as we work along today, but that is the homework.